Welcome to the Mobile Inverted Pendulum, or MIP track for the Capstone. For this track, your deliverables will all be in simulation, so you won't need to purchase any additional parts. However, the techniques you'll learn are designed to work on physical platforms, and we'll learn the sensory processing that you need to implement these algorithms as well. What this means is that the course is geared in a way to be implementable on a cheap physical platform of the kind that you see here. This cheap robotic platform has an inertial measurement unit, or IMU, which detects if it's falling and in general provides balance information, and it has motors on its wheels which you can send command inputs to keep it upright. But the learning and applications don't stop there. The mobile inverted pendulum is but a simple 2D cartoon, but it leads into much more complicated applications. The popular Segway device is essentially a mobile inverted pendulum, but it also has a third dimension, which allows its riders to turn, and it also has a more complex balancing algorithm that deals with unknown loads. Moving on, the rocket landing application, which has come to light recently, is also basically an inverted pendulum balance problem, but there the perturbation forces are orders of magnitude higher, and the control algorithms need to be much more robust. Human locomotion as well as animal locomotion can essentially be thought of as inverted pendulum balancing problems as well. So you learn how to apply the skills that you learn in this course to much more complicated real-world applications. There is a similar progression of learning as well, starting from a simple cartoon here, which is a single link inverted pendulum on a prismatic base, going on to more complicated plant models, such as this double pendulum. This model pictured here is called the Acrobat, where there's a single actuated joint at the knee, and this robot is able to stand upright. Robotic manipulators and legged creatures can also be thought of as many pendula connected through joints. The lessons you learn in this course can be applied to such systems as well. The material that you've learned in the previous courses in the specialization will be applied to the specific problem. In terms of modeling and control, in aerial robotics, you've learned how to control simple systems such as a point particle moving in space. And in the mobility course, you've also learned to model much more complicated systems using Lagrangian mechanics. You'll pull in all of that knowledge here for the mobile inverted pendulum. You've also learned in the aerial robotics course how to think about position control of a quadrotor as a hierarchical control scheme after its attitude control. And in the mobility course, you've learned about feedback motion planning as energy basins. You'll use all of that knowledge in this course as well. In the estimation course, you've learned about the kind of data that robots typically have to work with, and it's usually noisy. And you've learned about filtering algorithms that take this noisy data and make sense out of it to estimate the state of the robot. And you'll use all of that for the capstone. What you can expect is that per week you'll review some specialization lectures that are helpful. You'll have one new application-focused lecture per week. You'll have one or two programming assignments that will test out what you're learning and make progress towards the mobile inverted pendulum project. And your deliverables will be in a Matlab simulation environment. In the end, you can expect to be able to produce something like this simulation animation. Here what you're seeing is that the robot receives noisy sensory input, and what it must do is filter that data, balance itself, as well as try to position the base according to some desired trajectory.